All right, and here we are at the last one. So as I mentioned before, moment of inertia, rotational inertia, those similar words, more or less the same concept, is building up to angular momentum. And angular momentum is moment of inertia multiplied by angular velocity. And I don't know why. I'm sure it can be found somewhere on the internet if you're interested. But angular momentum, for whatever reason, is the letter L. So linear momentum, would have made sense. Maybe it's angular, or there's an L at the end. I don't know. But for whatever reason, angular momentum is letter L. And we have conservation of angular momentum. So we can set the beginning L equal to the ending L, and we can do sort of a similar trick than compared to what we had for momentum and players running into each other. The nice thing about this is we're not going to have spinning things run into each other. What we're going to have is a spinning thing change its shape. And so what's going to happen is we have some initial set of information that's going to change, and we have a way to represent that in our formulas. So the initial moment of inertia, rotational inertia, multiplied by the initial angular velocity, whatever that number works out to be is angular momentum, and then that's going to be the same total, but the values are going to change. So we use a prime or a tick mark, kind of looks like a single quotation there, to help show that this is some kind of updated or new or changed moment of inertia and not the original one. And this can't change and get the same answer without this other part changing as well. And so you've done this before, almost guaranteed. If you've ever been on a swing, a tire swing, something where you're spinning around and you stick your arms out and then you bring your arms in, you know you have that change in rotational velocity. In the book, they have a real nice example and show pictures and work it out where an ice skater changes her shape and spins faster or slower depending on how she's moving. The good news is I don't know the formula for the moment of inertia of an ice skater, but they give that to us here, so we don't have to worry about it. All right, so um, initially we've got a moment of inertia of 2.62 kilograms times meter squared, and then the angular velocity at first is 58 RPM. Now, normally RPM is not very nice to deal with, but the question they had revs per second, so that's actually not too far off. We'll have a small change at the end, but so far this is working. Okay, then later the ice skater lowers her moment of inertia by bringing her arms and tucking in. And you've seen them if you've ever watched figure skating where they sort of tuck in and start spinning a lot faster. We're going to see the same thing here. So moment of inertia, notice, is like 1/7 of what it used to be. And the only thing we don't know now is what's the new angular velocity. So omega prime, we don't know, but hopefully we should find soon. We can simplify a bit from here. The weird units from the moment of inertia will actually cancel each other. We're going to get RPM, so we do need to remember that we have RPM, and we'll have to get the revs per second in a little bit. But we can find omega by dividing. And again, you don't have to show the intermediate work. You don't even have to see the intermediate work if you type this all at once on your calculator. But we get that omega prime 2.62 multiplied by 58 divided by 0.368 gives us something like 412.9347, so on, so on. RPM, remember, is revs per minute. So we can say revs per 1 minute. And then because we want revs per second, we just need one quick conversion. So minutes on top to cancel, seconds on the bottom. 1 minute is 60 seconds. We cancel minutes. We've got revs left over, seconds left over. So as it turns out, this figure skater is which I imagine would make me very dizzy.